If you are asked to find time complexity from a certain program without running an experiment, how do you know? Hi coders! Welcome to CS Time channel. In this video, I will talk about introduction to Big O notation and time complexity. Let's begin!
Big O notation is a tool used to classify algorithms according to how their runtime or space requirements grow as the input size grows. Big O notation useful when analyzing algorithms for efficiency. From Big O notation, we can find time complexity as well as space complexity. Time complexity refers to the amount of computer time it takes to run an algorithm, while space complexity refers to total amount of memory space used by algorithm or program. This video focuses on time complexity. Time complexity is a concept that describing how the time it takes to run your function grows as the size of the input grows. From time complexity, we can examine worst case, best case, as well as average case. In this video, we'll see how to find the time complexity without running an experiment. Let's see the general rule for time complexity. The first one is find the fastest growing term or dominant term, and then take out the coefficient or ignore the constant. And then the last one is the time complexity from smallest to biggest. Let's see the constant time. Constant time can be expressed as O1 time or O of 1. This is independent of input size, or in this case I express it with n. Let's see the Big O complexity chart that you can find in bigocheatsheet.com. As you can see here, the y-axis here represent the time it takes to run function in microsecond, and then the x-axis here represent the size of the input. So if you run an experiment, for example, to find the complexity of a function, then you will see the chart will look like this. For example, you have 5 input or 10 input or 15 input or so on, then the time it takes to run this function is going to be the same. That is why we call it constant. Now let's see the example. For example, you are given a program like this. There is a given array from 1, 3, 5, 7, 9, and 10, and then your program only consists of one line. Output given array, access index number 1, which is here. So from this, we can understand that whether you are going to access index number 1 or number 2 or the last index, it will give you the same time, or the time is going to be constant no matter how many input you have. So it means here we only have constant. So the time complexity we have here is constant. So since constant is only 1, then we can put it 1, then under O we can put 1. So it will look like this, O1, constant time. Now let's see the next example. We use the same given array, and then you are given a function like this, and then the question is the same. So from here, we can understand that from the previous one that this is constant. And then the same thing for this. you assign variable number with x minus 1. No matter how big or how small the size of n, it's going to be not different in terms of time it takes for this job. So this is also constant. While the last one, return number, the same with this one, it will not affected by the number of input size. So this is also constant. So the time complexity will look like C plus C plus C. It's equal to 3 times C or 3C. Pay attention, we have a general rule here. Take out the coefficient. So we can take out the coefficient. The constant is only 1. So we can put 1 under O. So become O of 1 or O1 constant. Now let's see linear time. Linear time can be expressed as O(n) or O of n. N is the size of the input. Let's see the chart, the big O complexity chart for linear time. It looks like this. So the y-axis here represents the time it takes to run the function in microsecond, and then the x-axis here represents size of the input or the number of n. So if you run an experiment in a programming language, for example, you have a function, you run an experiment, then you will see that the chart will look like this. For example, for the number of input 5, the number of input 10, the number of input 15, 20, and so on, the time it takes to run this is going to be here, and then the time it takes to run 10n will be here, the time it takes to run 15n will be here, and so on and so forth. So the time it takes to run the function, it increases linearly. Now let's see the example. How does the runtime of this function grow as the size of the input grow? Given array is like this, and you are given a function like this. So now we understand that this one line, it doesn't going to be changed in terms of time it takes, whether the input size is 5, 10, 15, and so on. So this is constant. The same for here. This is also constant. The same for here is also constant. For the 4, if you take a look at this, for I equal to 0 to a given array dot length. So if the length is 5, it's going to be looped 5 times. If the length is 10 or 100, it's going to loop 100 times. So we will run it n times. Let's see the time complexity will look like. So we have C, we put it here, C, and then we have, for this one, we have n times C, because if we have 100, then we will run this constants 100 times. If we have only 10, then we will run this constant 10 times. And then the last one is C. Now, the result will be, we combine the C with C to C plus Cn. Now take a look at the rules. You have to take out the coefficient. So we can take out the coefficient. Here is the coefficient here, as well as the constant is the same. So we only have the n. As we can see here, linear time. Okay. So here we only have n. This n, we can put it inside the O, so it looks like this, O, and it's linear time. Now let's see quadratic time. Quadratic time can be expressed as O n squared time. N is the size of the input. And let's see the big O complexity chart for quadratic time, which is here. And y-axis, we understand that time it takes in microsecond. while this one, x-axis, represent the size of the input. So again, if you run an experiment on a function, on a certain function, to find its complexity, you will see that the chart will look like this. Say for example, if you only have 5 data, the time it take will be like that. If you have 10, the time it takes will be that. If it's 15, for example, the time it takes may be there. Okay, there, and so on. So the chart look like this. So the time it takes to run the function is quadratic, exactly like this. Let's see the example. How does the runtime of this function grow as the size of the input grow? You are given a 2D array like this, and then you are given also a function like this. Now let's see line by line. For num equal to 1 to 10, it means we will execute the one inside 4, which is constant, n times. Okay, and then this will constant because it will not affect by the number of the n or input. And then for this is will run the 4 inside will be n times. For the 4 inside also will run the statement inside of 4 n time. It depends to how many looping it asks. While for the statement here inside the 4, of course, it's constant. And then for the last one, it's also constant. So from this, the time complexity will look like this. N times C, because we will run C n times, plus C here, and then n times n times C, n times n times C, plus the last one, C. Then it will look like this. Cn, for this one, Cn, and then C plus C is 2C, and then this one, Cn square. Again, we have to pay attention on the rule. You have to find the fastest growing term as well as take out the coefficient. We can take out the coefficient. Yeah, we have the coefficient here. This is constant. This is coefficient. We take it out. And then this one also coefficient. We only have n plus n square. Now, pay attention to the first rule. Find the fastest growing term. We understand from the chart here that n on over here compared to on square, the fastest growing term is n square. So we will just use n square. So from this, we can put the n square inside the O. So it's quadratic time. Well, if you learned something from this video, please subscribe and like for more videos. Thanks for watching.